Thanks, Lo, for your introduction. Hello, everyone. This is Apoorva. And today I will be talking about microstructure identification in BPANI food can coating systems. BPANI coatings are used in packaging industry as internal can liners for food cans. They offer a sustainable replacement over the BPA containing epoxy coatings, but do not offer comparable shelf life. Hence, their investigation is of great interest from both commercial and scientific point of view. The overall aim of the project is to use microstructure as a guidance and find direct correlation to specific properties such as water uptake that can allow us to get fundamental understanding on the coating properties. But today I will be discussing the first part, which is pertaining to identification of microstructure and all the strategies that we adopted to simplify complex formulations. So just a quick overview on the BPANI coding systems. These are thermoset. Sorry. Hello. Sorry. The BPANI coding systems are thermosetting crosslinking blends, and they come in two variants: the chemical resistant type and the flexible type. So in addition to so they are mainly made up of polyester as the binder, and in addition we have several crosslinkers such as phenolic resin, benzoguanamine resin, and also the flexible type uses another crosslinker which is blocked IPDI type. So these are solvent-based formulation that need to be cured at about 200 degrees Celsius for 10 minutes to obtain cured coatings. To analyze the microstructure, we use atomic force microscopy in either contact mode or in peak force quantitative nanomechanical tapping mode. So this is a state-of-the-art AFM technique that allows one to get high precision force curves between the tip and the sample at each tap, which can then be used to obtain high resolution topographical images along with reliable complementary mechanical information. So here are the results for the height images obtained for the two BPANI coating variants. We observe that the morphology is quite distinct in these two variants. The chemical resistant type appears to have beads in the microstructure, whereas the flexible type appears to have island-like discrete domains in a continuous media. In addition, we also obtain addition images where the force of addition acts as a measurement of local hardness, such that soft surfaces gives rise to higher addition, whereas hard surfaces will give rise to lower addition values. We can see by comparing the two addition images that the contrast from the flexible type coating is quite high. So in order to further explore this, we can do the profile analysis. And for the chemical resistant type, 4 profiles were taken in different regions of the coating. We find that the addition values are quite comparable for all the profiles. This must indicate that the chemical resistant type coating is made of homogeneous material everywhere. But for the case of flexible type, we see 2 distinct values of addition. The discrete domain give rise to lower addition values and hence can be characterized as a hard phase, whereas the continuous phase gives rise to higher addition values and hence characterized as soft phase. Also, thermal analysis corroborates this results as we found a single TG for chemical resistant type coating, whereas we found 2 TGs for a flexible type coating. So from these experiments, we can conclude that the chemical resistant type coating appears to be homogeneous, while the flexible type coating appears to be phase separated at the scale of observation. At first, this difference in microstructure is not understood because the two coatings are empirically designed in a similar fashion. They both contain a similar weight composition, that is 70% polyester and the remaining 30% of by the crosslinkers. The main distinction that we investigated appears to come from the structure of the parent polyester. So the chemical resistant type uses a polyester which has low molecular weight, high amount of branching, and high aromatics. Such type of polyester will be very compatible with the resol type phenolic, which also have high amount of branching and aromatics. On the other hand, the flexible type uses a more linear and high molecular weight polyester. Indeed, we can imagine there can be some incompatibilities with aromatic rich phenolic and benzoguanamine. Another difference arises from the low hydroxyl value of the flexible type polyester, which can indeed introduce differences in the cross-linking reactions. To understand this, we looked at the functional group molar composition given in millimoles for individual component for a 50 grams of wet formulation. We observe for the case of chemical resistant type, the total functional group for phenolic and benzoguanamine are almost equivalent to the functional group from the polyester. Hence, we can see that this formulation is in stoichiometric balance. However, for flexible type coating, we observe that the functional group coming from the crosslinkers are far in excess to that from the polyester. In fact, they're 14 times. So this type of formulation is in stoichiometric imbalance and then can lead to asymmetrical cross-linking reactions or even self-condensation reaction between the cross-linkers. So at this point, we regarded that the root cause of phase separation in flexible type coating can be due to the structural incompatibility arising from the linear polyester and also the stoichiometrical imbalance of functional group present in the formulation. A direct characterization of full coating was found to be complex due to overlapping from several characteristic peaks. However, this is beyond the scope of today's presentation. So in order to deal with this, we needed to simplify the complex formulation into simplified model systems. For this, we devised several binary model systems and ternary model system, which will also allow us to study the effect of incompatibility. In addition, we also made these model systems in either stoichiometric balance or stoichiometric imbalance. And simultaneously, the changes in microstructure was followed with the AFM. So here are the results for a binary model system of polyester and isocyanate. We find for the first system, which is the equimolar system of polyester and isocyanate. And the second system here is a system with an excess of isocyanate. Here, the amount of isocyanate was matched to that found in a full formulation state that is blocked with ecaprolactam. So it is interesting to see that this peak also appears in the different spectra, thus suggesting that the isocyanate remains unreacted and in the block state. Further, this series is an extension to the previous slide where intermediate stoichiometries have also been shown. We can see that in all the height images, the coatings appear to be homogeneous. Hence, we can conclude that isocyanate and polyester appear to be compatible, and any excess of isocyanate will remain soluble in bulk of the coating and probably in an unreacted and block state. Another binary systems that I wanted to show were pertaining to polyester and phenolic and polyester and benzoguanamine in stoichiometric excess. Here, the amount of phenolic and benzoguanamine was matched to that found in the full formulation. It is interesting to see that both of these coatings appear to be heterogeneous. We also see that for the sample polyester-phenolic, regular circular domains appear. These have been referred to as the globular domain henceforth. For polyester benzoguanamine, we find irregular two-phase morphology where higher height features enclose lower height features. From the addition image, we can see that the enclosed domains are the softer domains. These height images suggest that phenolic and benzoguanamine are both incompatible with the polyester. It is interesting to note that none of these morphologies look comparable to the microstructure found in a full formulation. In order to move closer to the full formulation, we need to increase the complexity of the system, and hence ternary model systems were considered. Here, an equimolar polyester and isocyanate system was taken, and the amount of phenolic was varied from 0 to 6 times. The first system, which is technically a binary system, and as shown previously, is a homogeneous sample. However, with small addition of phenolic, we find formation of clusters that appear to be phase separated. Zooming in onto one such cluster, we can see that inside the cluster there are co-continuous domains which have been referred to as nodular domains. These nodular domains appear as the hard phase in a soft bulk phase. From qualitatively speaking, the morphology inside the clusters appears quite comparable to the flexible type full formulations. In the next two systems, where the amount of phenolic was slightly increased, we find that the nodular domains either grow in size or they grow in number. In the final system of this series, where phenolic is present in far X's, we find that it does not have nodular morphology, rather we see presence of globular domains. Another similar system was studied, but instead of equimolar, an excess of isocyanate was taken. In this series, the isocyanate is about 2.5 times that of the polyester, while the amount of phenolic was varied from 0 to 5 times. As expected, the first system, being a binary system, is homogeneous. In the next system, having small amount of phenolic, the system still continues to remain homogeneous. However, beyond this concentration, we observe formation of small nodular domains. When we further increase the amount of phenolic, we see a gradual increase in the size of these nodular domains until a peak concentration. Beyond this concentration, we observe a gradual transition of the nodular phases into globular domains. In the final system, we can see the morphology is purely globular. So with this kind of series, we were able to obtain a ternary phase diagram for the system polyester, isocyanate, and phenolic. So in this ternary phase diagram, the blue region corresponds to coatings with either higher composition of polyester or isocyanate, but with lower composition of phenolic. Such system will remain to be homogeneous. When the concentration of phenolic increases over 20%, the system will break into phase separation with either nodular morphology or globular. For intermediate concentration of phenolics, we observe that the morphology would be of the nodular type. But when the composition of phenolic is on the higher side, we will always observe globular domains. In order to characterize the difference between these two morphologies, addition images were obtained on them. Comparing these two addition images, we can see that the contrast in the sample with nodular morphology is quite high, while the contrast in the globular domains is lower. Also, we can see that since the addition values of the nodular domains are much lower than the globular domains, the nodular domains is a stiffer domain. Similarly, we can also say that the continuous phase from the globular is the most stiffer continuous phase. These kind of differences reveal that these two morphologies are significantly different from each other as they show physical differences. In order to understand the chemical differences, bulk FTIR spectrum were performed on these coatings. To obtain different spectra, the spectrum having similar polyester to isocyanate ratio was then subtracted from them. Such different spectra would then have peaks that are directly corresponding to the addition of phenolic in these systems. It is interesting to see that several peaks that correspond to the functional group from the backbone of the phenolics are present in these different spectra. with the exception of one peak, which is present at 1710. This peak is neither found in polyester nor in isocyanate or in phenolic single resin spectra. Hence, it must be arise due to some kind of cross-linking. Since the cross-linking between phenolic and polyester would give rise to ether bonds, it can be rejected. But it's likely possible that this peak is arising from a urethane linkage arising from the cross-linking reaction between phenolic and isocyanate. Comparing the two different spectra from the nodular phase sample and globular phase sample, we only observe subtle differences and cannot resolve them further. In order to see such differences, we need advanced characterization techniques such as AFM-IR that can allow spectroscopy beyond diffraction limit. The principle of this was already shared in the previous presentation, but just a short explanation is also covered here. So in AFM-IR technique, the AFM probe is in contact with the sample, is irradiated with a fast pulsating IR source. This causes the sample to undergo transient thermal expansions and cause the tip in contact to oscillate at its resonance frequency. The amplitude of this frequency was found to be proportional to the characteristic absorption. In this way, local spectrums can be obtained. Before moving on to the AFM-IR results, a quick overview of the peak assignments that was performed in order to chemically identify the components. The important peaks are 1688, which was previously shown to be corresponding to unreacted isocyanate, and another peak is 1710, corresponding to the urethane linkage from the cross-linking between phenolic and isocyanate. So here are the AFM-IR results that were performed on 3 homogeneous samples. The AFM-IR tip was moved on 2 locations, and the respective spectra are presented here. Further, a different spectra was obtained by subtracting the 2 spectrum. We observed that all the different spectra appears nearly flat, suggesting that the 2 spectra correlate quite well and reinforcing that these coatings are homogeneous. It is also interesting to see that in the sample which has higher amount of isocyanate, the peak at 1688 corresponding to unreacted isocyanate also appear higher as compared to the sample with lower isocyanate. Similarly, in the sample with a small amount of phenolic, we see a second shoulder appearing at 1710, corresponding to the cross-linking reaction between isocyanate and phenolic. So these results help to show that the AFM-IR correlates quite well with the bulk IR studies. And hence we can use AFM-IR in the characterization of the nodular sample. Here the carbonyl band arising from this study has been shown. The red spectrum corresponds to the continuous phase, whereas the blue spectrum corresponds to the nodular phase. We see that the red spectrum has a sharp shoulder at 1688, but in the blue spectrum, the slope is shifted due to an additional peak at 1710. So the additional peak can further be observed in the different spectra where the red spectrum was subtracted from the blue spectrum. As previously shown, the 1710 is a characteristic peak for phenolic cross-link with isocyanate. In this second analysis, I've shown the spectrum obtained for the entire fingerprint region. The blue spectrum corresponds to the nodular phase, whereas the red spectrum corresponds to the continuous phase. In black is given the different spectra obtained by subtracting continuous spectra from the nodular phase spectra. It is interesting to see that in addition to the 1710 peak, we get several other peaks such as 1483 and 1443, which are characteristic of the absorptions from the backbone of phenolic and isocyanate. These correspond to the methylene bends from phenolic and the CN stretch from isocyanate. So with both these analyses, we have good reason to conclude that the nodular phase appears to be a phase which has been cross-linked with isocyanate that develops, that phase separates as a hard phase from a soft continuous phase. It is also interesting to note that this type of morphology is deliberately obtained in segmented polyurethanes, where the linear or long chain polyester acts as a soft segment, whereas chain extenders, such as short chain polyols, cross-linked isocyanate, make up the hard segment. So this method was also used to characterize the globular phase sample. The blue is the spectrum obtained from the globular domains, whereas red is the spectrum obtained from the continuous domain. Further, the different spectrum is shown. It is interesting to see the peaks that are characteristic to the phenolic backbone appear in the different spectra. But for the peak corresponding to the urethane linkage, we see a drop in intensity. What this suggests is that the globular domains are rich in phenolic, but devoid of isocyanate. This makes us to suggest that the globular domains must be a self-condensed or self-curing product of phenolic cross-linking reactions with itself. Further to this, we gain several correlation between the phase separation found in the full formulation and the nodular morphology that's been discussed here. We observe that the characteristic two-phase morphology in the full coating appears only when the coatings are cured above the deblocking temperature, suggesting that the isocyanate has a huge role to play in the cross-linking. Also, quantitative stiffness maps were obtained between the nodular phase sample and the two-phase flexible type sample. And we observed that the two phases present in these two coatings also show quite comparable adhesion values, suggesting they are physically quite similar. Also, by following the cure reactions and obtaining a different spectra, we observe that as the curing proceeds, the peak corresponding to free unreacted isocyanate decreases with simultaneous increase with the formation of urethane peaks. So this suggests that there is a close correlation between the properties of the full formulation and the modular system obtained by cross-linking polyester-phenolic and isocyanate. In conclusion, we have seen that the two variants of the BPANI coatings, out of the two variants, the flexible type gives rise to heterogeneous coating, which has been shown due to structural incompatibility and also stoichiometric imbalance. Then we've investigated the effect of individual components, and we found that the isocyanate gives rise to homogeneous coatings. Any excess of isocyanate will remain dissolved in the bulk, whereas phenolic and benzoguanamines inherently gives rise to heterogeneities. The amount of phenolic plays a strong role in determining the final morphology, which could either be nodular for lower amounts of phenolic or globular for higher amounts of phenolic. The AFM-IR on these domains has shown that the nodular phase is a phenolic plus isocyanate phase, whereas the globular phase is a more phenolic plus phenolic type of phase. We have received good correlation between the physical and chemical properties of the nodular phase and the full formulation flexible type coating. Also, we've shown here that by tailoring the stoichiometry of functional group, the final morphology in these systems can be controlled. Thank you.
Thank you very much, Apoorva, for your nice presentation. We have a couple of questions that have been posted in the chat. Let me read them first. The first question that was about the ratio of your what is the ratio of your polyol to that of your cross-linkers in the IPDI?
So what is the ratio of the
polyol to the cross-linkers?
So in the full formulation or in model systems?
Let's go for both.
Okay, so in the full formulation, which is being shown here, we have the isocyanate, which is the IPDI, which is 4.5 times that of the polyester. Sorry, did I answer the question?
I hope so.
So are you asking, sorry, is this for weight composition or for functional group composition? Because they are quite different.
Why don't you generously answer both cases?
So in the full formulation, we have by weight composition, the polyester is 70% and the isocyanate is 16%. But with functional group distribution, we have polyester, which is, so this is in millimoles, so 1 millimoles in 50 grams of wet formulation, and IPDI would be 4.5 millimoles.
I hope that answers the question. There was also another question, if you carry out any formulation with aromatic crosslinker.
No, we haven't.
Do you think that would be interesting? Or
so I think the goal here is to take the current formulation and try to investigate that. So with respect to that, the crosslinker in the original recipe is IPDI, and also phenolic and benzoguanamine also act as crosslinkers. So.
Okay, there is another question for your presentation. The question is, do you think in some AFM images at the beginning of your presentation, disrupted morphologies are caused by air release? And whether did you use any leveling agent?
So there are no additives in the formulation. So indeed we have, for example, in this type of morphology, it could be something what the question suggests, and we have not used any leveling agent because it doesn't come up in the stiffness value. So it probably is more of a physical phenomenon from maybe solvent evaporation or something.
Okay. I think I covered the questions that were posted in the chat. If there are any more questions for Apoorva, please post them in the chat and she will answer them as they are posted. And thank you very much, Apoorva, for your nice presentation.
Thank you.
Our next presentation comes from Leicester University of Leicester, and Craig Melton, are you there? Yes. If you can share your screen, that would be fantastic. He's going to talk to us about dye-containing coatings for corrosion sensing applications.
Yeah, can you hear me?
Yes, we can hear you.
Excellent.
Thank you.
And you can see my presentation?
Yes, we can see your presentation.
Great.